standard, I mean, standard is, well, they're at college level, we would say 3. Some colleges will say Calc 4. Calc 4 is typically more of an algebra-based course, modern algebra, that sort of thing. But definitely 3. So in a college, they will do 1 semester is the year, your senior year high school would be 1 semester of college. So they take that semester course in at college, and they decompress it into a full year for high school. So if you take the high school, which you will, if you take the high school calculus course, then you've really taken first semester college.
So I don't have to do a second semester of calculus?
Hello? When we offer AP calculus, that's because you'll take a test, and that's when you get credit for that 1 semester of calculus.
Wait, so what is the hardest math you take?
No, this is
mean,
science. You just put it up.
Yeah, I would say any of them are. Well, I mean, you're talking to a math person, so conceptually wise, the 3rd year of calculus, that was 3rd year of calculus, what I was showing you. That 3rd year is hard for a lot of people, myself included, because you have to figure out what you're integrating from and to, and so you have to think in 3 dimensions in order to figure out, wait, the x-axis would go from 0 to 1, but the y-axis would go from -1 to 0, and the z-axis would go from -pi to pi. I mean, it can get complicated like that. It was absolutely more challenging than Calc 1 or Calc 2, but I got an A in it. It was like, okay, a little bit extra mental thought behind it, but I wouldn't say it was hard. But plenty of people fail calculus left and right in college because they just don't understand the amount of work it involves. If you understand how much work and you do the work, you'll be fine.
But on the bright side, if you're last year of math, you're not going to take a math
Right.
job.
Right. And the other thing too is that you're talking about high school or college.
College.
So I would say most degrees do not require calculus. If you have a non-technical degree, then college algebra is just trig, one step above pre-calculus is what they would call it now. Most high school students that are you guys in advance, if you take calculus, then you would laugh at a college algebra class. It would be just, okay, this is what I did the year prior. And calculus, you're going to use your pre-calc skills every single day. What's up, Ben?
Oh, the ceiling last time I checked.
I have a question though. Why do you have to have calculus to explain the area of a circle? Because if you just because it's basically if you just divide the circumference by the diameter, you get pi every time.
Yeah.
So then if you just get 2 pi and then 2 pi r.
Well, remember, you got to prove this.
Well, yeah, but I mean, all we have to do is just.
So I told you that the definition of pi is the circumference divided by the diameter. So where did area come in?
Well.
And that's the hard part. So there's going to be plenty of and I did it in pre-algebra as well too. I mean, I showed you an idea of where they take a circle and they cut it into a lot of little tiny pieces. So they take a circle. This is the standard pre-algebra proof of why area circles pi r squared. So they take a bunch of these little pieces right here, right? They cut it up into equal number of those parts. They take half of them and they stack them up like this, right? The issue is that the bottom isn't flat, it's curved, right?
Yeah.
And then they say they take the other half and they stick them in between. So this distance right here, from here to here, ends up being your radius, right? Because you have half the diameter's here, half the diameter's on the top, right? You get this basic idea that this is a parallelogram, right? The parallelogram is base times height, right? Area of the parallelogram is base times height. So let's see, the base would be the radius, right? The height would be, well, the distance from here to here, well, that would also be the radius, right? And where's the other part come from? Well, that would just be r squared, right? So where's the pi come from? Well, the pi comes from the fact that the radius, right, is the circumference, right, divided by the diameter. right?
And then the diameter is 2r, so it's c over 2r.
Right.
Okay, makes sense.
And that's where they justify this form. But once again, this is curved. This ain't flat. So basically, it's a we call it a hand wave proof. Well, not even that much. We just call it a visual demonstration of potentially where it comes from. But calculus will allow you to calculate the area. This is first year calculus. Will allow you to calculate the area of any two-dimensional shape as long as you can write a formula for it, which you can. Right.
I mean, you can do that in many.
And that's how it's proved in calculus. And you will do that in calculus.
Are we going to use E?
We'll be using that in pre-calc, I believe is when the E. Do you understand what E is?
Yeah, 2.18.
Wait, but what is it?
It's like the definition of like all living things or something.
All what?
Like it's like the definition of like all shapes or something.
No.
Something like that. Like I heard the definition of it.
If we have time at the end here, I'll play you a quick video. Okay, question on homework. I don't.
32.
Period 32. Let's take a look at 32.
It's 32. Oh, yep.
Did I share this yet, Ben, or you got black screen?
I see the back of your chair.
All right.
I think I got it right, but I'm probably way wrong. Even though I don't remember what the wrong.
Oh, we're just trying to prove that the diagonals of a parallelogram are good.
Prove 512, the diagonals of a what?
Parallelogram are congruent.
Rectangle.
Rectangle
Oh,
congruent.
not parallelogram.
All right, so Ben, draw me a rectangle.
I do
And-
not have the ability to do that.
All right, then we're going to draw an escape. And at the very top, hit stop share and then face it so it's facing the screen.
Okay, wait.
Stop share, right, red.
Okay, got it. Stop share, and then what?
Face the camera this way.
Mouse.
All right, Ben, you see my rectangle? Your water ball is probably away. Closer.
Okay, I'll move closer.
See my blue rectangle?
I don't think the black's helping.
Yeah, I
And-
don't think the black is helping.
Ben?
Whoa.
Here you
You
go.
see my rectangle? All right. So we draw the two diagonals, right? I'll call it A, B, C, D. And we need to prove that AC is it's the
I'd
congruent,
recommend putting O in the middle, by the way,
right? Sure. That'll
because
work.
then you'd use the.
I'm not even going to use that. I'm going to do it a different way. Well, we know it's a rectangle, so we know that opposite sides, because it's a parallelogram, are congruent, right? And I'm going to split the two triangles apart. I'm going to split this triangle. So I'm going to split ADC. I'm going to split it from so ADC from BDC. Did I draw that right? Yes, I did. Okay. And we have that. We have that. We have this, and we have this. We also know it's a rectangle, therefore it is
90 degrees.
90-degree angles. There's our A, SAS, and we're done. CP, CTC. That's one way of doing it.
Oh, my way.
Oh, I kind of did a similar way-ish.
I did vertical angles.
So, which one you want? Top,
Wait,
bottom,
hold up.
left,
What are
or
we
right?
trying to prove? AB is congruent.
Well, we
Wait.
got to prove this whole thing.
Oh,
though.
right,
That's
right,
the
right,
issue.
okay. Yeah.
Now,
Well,
if you wanted to prove
then
that
I just-
this was congruent, you can, and that's it would just take double the
yeah,
work.
that's what I did.
Okay. So that's how I would do 32. I want to say we talked about it, and I gave you the hint that you should split it apart.
Well, I knew that originally. I just had a different way where I found a way to that angle.
There are other ways of doing this one for sure. For sure. All right.
Yeah,
Anybody
I
else?
said
Question?
I said line AC was a bisector because AD and BC were parallel angles, and that was easily
Absolutely.
provable.
Absolutely. So maybe Jack, if you would use that this is a bisector.
Yeah.
The issue is that we don't know it's congruent, so I got 3 tick marks here, and then 1, 2, 3, 4 for that. 1, 2, 3, 4, and then you could once again really quickly that the 2 are congruent. But I would still even use this, then we get SSS out of that, right? Yeah, but I'm saying if I split those 2 triangles apart, then I would get a.
What you can get an SSS, you're trying to prove.
I would because. Oh, you're right. Never mind. Ignore the SSS part there. Okay.
Okay.
All right, 1 through 19. Here we go. I'll just call out the even ones since the odd ones were in the book. All right, the table of pain. That's a pretty darn big table. I'll just say that table of pain would be a good thing, especially for your test, to have handy in your notes. If you're wondering, what would the questions look like? A couple of them be your standard. Hey, it's a square, so are all the diagonals of the square, do they bisect each other? And if you have this table, it will tell you that sort of stuff. All right, so number 2, it's everything's checked. Number 4, everything's checked. Number 6, just the rectangle and the square are checked. Number 8, the rhombus and the square are checked. And number 10, the rhombus and the square are checked as well. Yes, we good?
Yep.
All right.
Yes.
Now we'll pick it up. Go ahead, Ben. What?
Number 8, what was that?
Okay. Oh, number 8 was rhombus and square. Number 12, I believe X is 4.
I'm not there yet.
Oh, I thought you
But yeah.
said.
No, I just want to do just the table thing. I'll call out all the other answers.
Oh, okay.
All right, even though the odd ones were in the back of the book. So 11 should be 25, 65, 65, 90 in order 2, 3, 4, 5. Number 12, X is 4. Number 13, X is 10. Number 14, in order 2, 3, 4 would go 18, 72, 72. Number 15 is 13.5. Number 16, Y is equal to 2. Number 17 in order 2, 3, 4 goes 32, 58, 58. Number 18, X equals 9. And number 19, Y is 0.5 or a half. And then we did 32. That was it.
Most of those. Yay.
Most is better than none. Have you been in McCall's classroom? Is it loud or not loud?
Well, I mean, it was.
It was.
I can't imagine that getting any better.
It has to. It was last.
I mean, they haven't even done any real hammering or anything like that,
Yeah, well, what's been the loudest is when they're taking out the stone.
Oh, yeah. All right, let's see. Yeah, it would be a bad idea to have the test on Tuesday, so we will have it on Wednesday. I'm going to give you a full review tomorrow, and then we'll do a skill review on Tuesday. So I'll give you a full review, what the test will look like on tomorrow, and then we'll just concentrate on the skills on Tuesday, and then take the test on Wednesday. We're really good on time, and what I would like to do after the test, there's not an algebra review for this chapter, is that we just go over the whole book. We'll do half the book on Thursday, half the book on Friday of what we've done so far, and just do a quick skill review, excluding chapter 5 stuff. So we'll do chapters 1 through 2 on Thursday, 3 or 4 on Friday, and that way we have it fresh in our mind. We will be taking in the near future a test. It doesn't. It's not like a state test or anything like that. Most schools do this. We're getting a late start on it this year because we were setting the program up. But it's going to be a math and a language arts test, and we usually give it at the beginning of the school year and the end of the school year. How much do they know at the start, how much do they know at the finish type thing. It's a cumulative math test, so it's going to test everything from calculus on down type thing.
So then we're just gonna be like, what?
Well, as soon as they ask you a trig question, you don't know it, they're not going to ask you a calculus question type thing. So It's one of those tests where like, I've never seen this before in my life. You take a guess at it, you get it wrong, and they don't ask you another question.
But if I get it right.
Get it right, that's always the issue,
Oh,
right? And so for smart kids, a lot of times, even if, I mean, I remember
I bet I could figure out.
I remember giving this particular test and to some of my kids, and there would always be a question that would have a weird symbol. And the kids were like, what does that symbol mean? I was like, oh, I don't want to tell you because then they're going to be guessing. But I would have kids literally like just try to figure it out. What the heck could that even mean? And they would
Wait.
figure it out, right? And then it would ask them a harder question, you know?
Oh, I see.
There's no school on Monday.
There is no school on Monday.
Why?
Teacher work day.
Thanos.
Oh, okay.
Okay. Homework. A pretty easy, quick day. 2 theorems, and they're both pretty easy. Well, the proof isn't easy, but the theorem is easy.
Find this theorem and
Hey, you don't have to look too hard. There's only 2 of them.
All right.
Is there page 190? But don't look ahead because then you already know how the proof goes, and it kind of spoils the fun of the thought process. All right. The last class was on special quadrilaterals. There's nothing special about them. They're just different types of quadrilaterals. Let's see. We talked about rectangles. Remember, rectangles are parallelograms, so you get everything that a parallelogram has. That means the diagonals bisect each other. Opposite sides are congruent. Opposite angles are congruent. Consecutive angles are supplementary. Opposite sides are parallel, and I think I named all 5 of them. But we get this special one. We get this theorem from last time. It said that the diagonals are congruent. This was question 32. The next one we talked about, which were squares. Squares are kind of in the middle between rectangles and rhombus. A rhombus, we proved that the diagonals are perpendicular, right? A rhombus is not a rectangle, right?
Is it?
Or I should say some rhombi are rectangles, but most aren't. Turns out the square's in between the 2. So everything that a rectangle has, a square has. Everything that a rhombus has, a square has, right? Because squares are rhombi.
The squares have everything.
Yeah, squares are.
And oh, by the way, all 3 are parallelograms. But those were the 2 theorems we had from last class. We also had this other 2 other theorems, and it said something about to the effect. Let's see. The first one had to deal with triangles, but remember we made a parallelogram out of it to prove it. This is a key. We will use this a couple times this year. It's easily forgettable. If you have a right triangle, not just any triangle, a right triangle, and you draw a segment from the right angle to the midpoint of a hypotenuse, that the 3 segments that are now constructed, well, they're all congruent to each other. Pretty remarkable theorem. All right. Okay. The other theorem we had was if you have a parallelogram and you have one right angle, it is a rectangle, right? So basically what it says, if you have one right angle and it's a parallelogram, then it's a rectangle. And the last one we had is that if you have a parallelogram and 2 of the sides are congruent, then it's a rhombus, right? All right, so today's class, we get our last special quadrant, not plural, but it's one last one, but it comes in 3 flavors, so plural. And that is a trapezoid. All right, so write this down, please. Hopefully you remember this from pre-algebra. If you are a trapezoid, you have exactly 1. Now remember, parallelogram has 2 pairs of parallel sides, but a trapezoid only has 1. I know. I decided to, between second period when I taught it, I was like, I don't want to hand him the sheet. So a trapezoid has exactly 1 pair of parallel sides. So if it has 1 pair of parallel sides, it needs to be indicated. So the book will indicate it either with the word trapezoid, or they will
Just indicate that there's 2 parallel
how are they going to do that?
with the arrows.
Okay, so they're going to put those red arrows, right? Red triangles, whatever you want to call them. Okay, so there's a trapezoid, and remember it's just 1 pair. So if it had 2 pairs, it would be a parallelogram. This is not a parallelogram. So all those things we got about parallelograms, we cannot use for trapezoids. Trapezoids come in 3 flavors, right? This is the first flavor. We'll call this the plain Jane trapezoid right here. We give names. You should remember this from pre-algebra. We give names to the 2 parallel sides. You remember? It was used in the formula for the area of a trapezoid. And they are opposite each other.
Bases.
They are called the bases. Okay, so the bases are the 2 parallel sides. We had that. If you remember the formula for area of a trapezoid, anybody?
6. No,
It was something very complicated.
It was complicated.
it was like pi.
We'll get to. There's no pi involved.
Wasn't the area of a trapezoid A plus B plus? No, wait, that's perimeter. I don't know.
That's what it is.
I should have done better.
We would say 1/2 of the whole thing, but we would say you add the 2 bases
And then
in parentheses,
multiply them.
multiply by the height, and then divide by 2. We call the 2 non-base sides the legs. So using the same words as we did with triangles and right triangles. We have the legs and the hypotenuse. Now we have the legs of the trapezoid. We had base for triangle. We got base for trapezoid.
Why are they called legs? They don't even touch the ground. They're just there.
Yeah, agreed. All right, so this is plain Jane trapezoid. Now we have the 2 special types of trapezoids. The first one, the trapezoid, the 2 legs will be congruent. We're going to call this trapezoid. Anybody want to guess?
Congruent triangle. Congruent trapezoid. Special trapezoid.
Anybody?
Good. Happy trapezoid.
If 2 sides are congruent, we're going to call it.
A parallel.
Oh, isosceles.
We're going to call it an isosceles trapezoid.
But you can't have isosceles.
I know, isn't that weird? They're like they should have better names. So isosceles trapezoid, just the legs. Now, the bases will not be congruent. If the bases end up being congruent, well, then you got a parallelogram.
Yeah.
So the bases will never be congruent. The legs can be congruent, but
Well,
the bases can never be congruent.
And if the sides aren't, right? The
Well,
legs aren't.
remember, it's a parallel. It's the 2 leg or bases, sorry, are parallel.
Oh,
So
yeah.
I don't care even if I
Even
draw
if
it
you
like
have
that.
one
If they're
side,
congruent,
yeah.
when you play connect, right, it's a parallelogram, right? The legs, however, can be congruent. And then the last one, it's going to have 1 right angle. Therefore, we're going to call it a.
Right trapezoid.
Now, it's a misnomer to say it's 1 right angle because it actually has.
2.
Right, and then we get that from that one theorem that said if 2 parallel lines cut by transversal, this is 90, and the other one's 90 as well too. So the pictures will never show the second angle as being 90, it's 90. So here's your 3 types of trapezoids. Our book will spend a lot of time on isosceles and a fair amount of time on right isosceles or trapezoid.
What do you call the first one?
Just a trapezoid.
Why does everything that's 90 degrees called right?
That's a good question.
Because they're always right.
That's a good question.
If you get in an argument with the right triangle, it's going to
No, it isn't. I just push it off the table because it's a triangle.
be. What if the triangle's smarter?
The triangle's not smarter than me, Jack.
All right, I'll remember that on the proof I give you.
What?
That will be about a triangle.
That's different. Triangles on the proof, that's you writing down the triangle thought. The triangle by
Have I
itself.
looked at what the proofs look like? I don't think I've looked on yours. I've looked at the other people's. I had to actually make up a proof for them. All right, let's do a proof. Okay, so clearly we have what shape? What kind?
Isosceles.
So we got an isosceles trapezoid. What are we trying to prove?
X and Y are congruent.
So we're trying to prove that the base angles are congruent.
But that's easy. Just use isosceles and boom, you got it. Yay.
Yeah, but it's the isosceles triangle. It's not the isosceles triangle.
Okay, so what's your
We
thought,
can't make
McKinley?
an isosceles trapezoid. We just have to split it again.
Okay, so how do you want me to split it?
Wait, I know how to do it.
Thank
Go ahead.
So can you just construct 2 lines that make a triangle? Wait, never mind.
You can't make a triangle because you cut through them.
Could we make a triangle here?
We could
So what do you want me to make?
make from like B go up, or just like draw diagonal XA.
Okay, so we could draw XA. What's the problem with that? I mean, our standard technique would be to show that 2 triangles congruent, called CPCTC.
Yeah, but the true triangles are not
Well, I got S, I got reflexive, got another S.
And you have the
You're not
congruence.
trying to prove that you're higher.
Well, I mean, the other thing is, I mean, just think about it.
You get
Are the
yeah,
two bases the same or are they different?
they're different.
Yeah, that's why we can't get congruent triangles out of that.
So the other thing you could do is make a triangle like at the top, like go like make a point up here and then connect B and A.
Okay, I like that. Now what?
And then the only thing you can do is make an isosceles triangle.
So if we could somehow prove that this was congruent to this, then we could get, because it's isosceles, that would be congruent to that.
Yeah.
Maybe that can be done.
Well, we would have to prove that also whatever the top one is, that's Z, I guess, is ZA is congruent to AY.
Right, and that's going to be the issue. Okay. Your first thought though was kind of close to the right idea. So what they're going to do is they're going to make they're going to still do CPCTC. All high school proofs are CPCTC. They're going to still do it. They're just going to draw their triangles a little differently. What they're going to do is they're going to drop a diagonal down from B, a perpendicular down from B straight down and from A straight down. Let me catch up.
Makes sense.
So they're going to drop from B straight down perpendicularly and from A straight down perpendicularly. And if they could somehow show that those two little triangles now are congruent, then we got that X is congruent to Y.
Hypotenuse leg.
Where do you see that?
Maybe. No,
I mean, maybe, but we don't.
Well, we certainly have the hypotenuse.
yeah, but you can get a leg because you can do angle, side, side.
Okay, well, we need a leg.
Well, can we say that BP is parallel to AQ?
Yeah.
Or that BA is now parallel to PQ?
Why don't we just say they're congruent instead of parallel?
Well, yeah, that's what I meant. I meant that.
But
BA is parallel.
why can we claim that BP is congruent to AQ?
Because it's a parallelogram now.
Even easier than that. Why can we?
Oh, because it's a triangle, a rectangle now.
Okay, we're going to get to that here in a second. But why can we say that BP is congruent to AQ?
Well, yes.
Yeah,
We'll save that for our next thought.
but you can use parallelogram, which means two sides are congruent somewhere.
Where did I make BP congruent or parallel to AQ? I just said drop down a
Oh, wait, they
perpendicular.
never touch each other. So
Well, how do you know that?
because they're parallel lines.
How do you know? Well, how do you know they're parallel?
Because of the parallel lines.
I didn't make them parallel.
You can make them parallel or perpendicular.
I could make them parallel. I
Yeah,
could do
you gotta
that.
make
That
them
actually
parallel.
would be more helpful.
Yeah.
This is actually easier than you think. You're just kind of not thinking through it. If I draw this, you'll get it immediately. Here's BA, and it's parallel to XY. If they're parallel, what do you immediately know?
They're congruent.
If they're, no, they're not
No,
congruent.
congruent. You can cut them.
Cut by
If they're
transversal.
parallel,
They
what
never
do you
touch each
know?
other. They never touch each other.
What does that mean in,
They go
They
on
never
first.
intersect.
so what does that mean in regards to BP and AQ?
They never.
They never intersect because they both go through the parallel. It's 2 points that go through parallel lines, so they're congruent because if to any point on a parallel line that goes to another parallel line is congruent to another.
We
point
didn't
goes
say
to-
that, but that's what we're going to
Yeah,
use.
that's the theorem that we got.
We have a
whatever.
theorem that says that if you have two parallel lines and you find any 2 points,
Oh yeah, theorem 5/8.
5/8 says what?
If two lines are parallel, then all the points along one line are equidistant from the other line.
Well, if they're equidistant, what does that mean?
That means they're congruent.
That means they're congruent, right? And that's
what I was
5/8.
trying to say.
All right,
Oh, yeah, 5/8. I forgot about 5/8.
all right. Well, that's cool. So
Well, you
now
can
we
do
can,
that for,
now we do have hypotenuse leg, right?
Yeah.
So now we can get the X is congruent to Y after we say that. Well, we got a problem now. I just drew a line through B and A.
Oh, wait, you just have to do the repeat thing. Be like, hey, then repeat.
Yeah,
math,
yeah, but
please.
what-
Not on this one.
But you can, but yes, you may. No, wait, maybe.
B is congruent to A now.
Oh,
Oh, now we know that now we know that those are parallel, right?
Do we know they're parallel, or do we have to claim they're parallel?
We have to claim they're parallel first.
Well, how can we do that?
If we know they're parallel, then we can get it. But well, actually no.
We can use theorem 5/8
Well,
again.
You were claiming a second ago it's a rectangle. So
Yeah,
well, how can you
You
claim
don't
it's a
need to know
rectangle?
they're parallel to get the answer.
All the angles are
oh, because
90 degrees.
there'd be 190.
There's one 90-degree angle, therefore it's a rectangle. And how is that going to help us?
Well,
Now we know that angle PBA and angle QAB are equal. They're congruent. And because we know angles XBP and YAQ are right next to said angles, you add them up together and then they equal the
They
same
are
thing.
congruent because of the previous triangle. Good job, Ben. So they are congruent because of the C. Therefore, Ben said that both of these must be 90. You guys said it was a rectangle. Therefore, well, how can we claim now that B is congruent to, say what? What do you mean addition? Postulate 4, which is the angle sum. You just showed me that the little piece is congruent to little piece, CP, Ben says that's 90, therefore, and the sum of those two, you're adding the same thing on both sides. So angle addition postulate rather than angle sum. But
Love me some qued.
right, quad Eric demonstrandum. Cool. By the way, we proved 518 that says that if you have, now be careful, I made it red and underlined in bold. This is only for an isosceles, not for a right, not for a plain Jane. But if you are if you are an isosceles trapezoid, then your base angles, be careful with that. It's not saying that B is congruent to X, right? It's saying the base angles, which is not very descriptive. So make sure you understand which ones are the base angles. So X is congruent to Y, B is congruent to A. So there's your first skill. This one will be pretty easily done. For some reason, they don't give this next proof, but they should. What do you know about B plus X?
B plus X equals 180.
On any trapezoid, not just isosceles. Why? Because parallel lines cut by transversal. Okay. So that's true. And then also, since it's quadrilateral, all them added together is 360. N minus 2 times 180. They don't prove that one, but why is what? I don't know. Well, remember, I took my iPhone and I'm holding down the page, and the page is curved a little bit, right? Close to the, I bet this is on the page on the left where I took the picture at. That's why it's curved there. If it curves on this side, that means the page was on the right side of the book, and this one, it's on the left side. Okay. This one's a pretty easy definition. It's the medium of trapezoid. It does not combine the legs. It doesn't combine the bases. It combines the legs. So if you go from middle of the left leg to middle of the right leg, you've made a median of the trapezoid. It's not claiming that SM is equal to SR. That's true on isosceles. But in just general, we're just saying that, well, it connects the middle. If it is an isosceles trapezoid, though, SM is equal to RM. Or I should say all four of those pieces would be congruent for isosceles. All right, now we're going to prove something hefty. I did not prove this in the other class. I just said, write this down. It's too complicated. It's not too complicated for you. So I got a trapezoid. Doesn't say isosceles, doesn't say right. It says a trapezoid with the median MN. It's kind of hard to see. I want to show you that the median is parallel to both bases.
Okay.
And I want to show you that the median is half the sum of the other two legs. Keep saying legs, I mean bases. Add the two bases, divide by 2, that's going to mean the median. Okay, that's what we're trying to prove. That it's parallel to both bases, and if you add the two bases and divide by 2, you get the median. It's a lot to prove, All right, the book shows 3 different ways of doing this. I'm not sure why they chose 3 ways. I chose the least complicated one. No one would get this. Is a hard proof. So here's what they do. This formula kind of sort of looks like something we've seen before. It looks like
Area of a trapezoid?
no. Oh, okay, I'll buy that. Yeah. It kind of looks like, but we haven't had
midpoint, kind of. Like
yeah, something about that. It kind of looks like that triangle one that we just had.
Oh.
Where if you have the median of a triangle is equal to half of the base.
Yeah.
Okay. So the way they prove this, or the easiest way, is Well, they make that triangle. They make a triangle, right? What they do is they do that. They make a triangle. But they make their triangle, the third side, go through the median of one side. I'll show you the logic here in a second, but that's their construction. So if you ignore this top right-hand piece, you got that triangle where, hey, wait, it's a median. So this side is congruent to that side. I'm pointing to S, M, and MP. And we know from that other theorem that if you have three parallel lines where a transversal is cut into congruent parts, what can you tell me about this part of the red and this part of the red? They're congruent. So we get that and that. Okay, let me get caught up here. Now, what they're going to do next is they're going to show that these two triangles are congruent. How in the world is that possible?
Well, you've already got, well, I mean, you've got two sides on one.
We got an S and an S.
You need to prove that NO is congruent to SM.
We got that 1, 2, 3 is congruent to 1, 2, 3. I'm trying to show that
No, well, I mean,
T and Q is congruent to S and R.
Well, you only have to prove S and R and O here.
Vertical angles. See it?
oh yeah.
Now, I didn't write all the steps to proof because you'll see I run out of space. So it's easy to see that this triangle is congruent to this one.
Yeah,
You see that?
gotta prove-
SAS?
Yeah,
Okay. Why did I say ASA?
because you have vertical angles. So
I don't know why I wrote
it's
ASA.
SAS.
It's SAS. So ignore that. It should be SAS. Okay. Okay. Well, what good would that do? So the next thing is I'm going to say that N is the midpoint of ST. Well, duh, right? And therefore that those other tick marks are there. Now, why can I say that it's now parallel?
Because of theorem 6.3.
What is 6? Wait, we're not in chapter.
No, because of the theorem that like if you have a median that cuts the two sides, then the two sides are parallel and it's 1/2 of the side.
Notice I now have a triangle. If this goes through the midpoint of this, right, and the midpoint of the red, then it has to be
Wait,
parallel.
now that we have OT is congruent to SR.
I don't forget what theorem that was. 511.
Wait, now that we have OT is congruent to SR, now we can say that PO plus OT equals 1/2 of PO plus OT equals MN.
I think
And then
I
you
know
can
why you said
exchange
ASA,
those.
though.
Why did I say SA?
Because couldn't you say that alternate interior angle so you could
Oh,
SR
yeah.
and
So I could have said that that is congruent to that, and then vertical angles ASA. But either one, ASA or SAS. Good job, good catch there. All right, this is getting kind of messy.
But now you can say that since PO.
Oh, by the way, I'm done with half the proof, right?
Wait, so now you can say since 1/2 PQ plus 1/2 PQ plus QT equals MN, then you can substitute SR for.
That's what we're going to do. But let's write it a little bit better. Let's look at the triangle and set up that equation. So we want to say that 1/2. I don't know what you were saying, but I think you want to say MN is. I'm sorry, 1/2 of PT is equal to MN. Yes.
And you can say 1/2 of.
All right. So let me say that.
PQ plus.
That's
QT.
theorem, whatever that is. What's the theorem where we got that one from?
I
I don't know. 511 as well? Yeah, that's 511.
yeah.
That's the other half of 511. Okay. So what we want to do now is say something about PT. Well, what's the obvious thing you can say about PT?
It's PQ plus QT.
Okay, so you know, segment addition postulate right there. So there's the segment. I'm going to put this all because I'm out of space here. So there's the segment addition postulate, that first part, right? And then what I'm going to do is, well, we don't really want QT in our formula because that's a made up thing. QT, because we just showed that these two triangles are congruent. QT is congruent to, because of CP-CTC, okay? So those two
Well,
things,
you
segment
also have
addition,
to-
comma, CP-CTC.
Wait, you have to say that QT is congruent to SR by CDCTC though.
I do, and this should say comma CP-CTC, it doesn't. So that's the one true mistake here, is it should say comma CP, or substitution. Did I ever say that?
Yeah, you said, well, substitution for SR already.
Do I ever say that SR is equal to QT above here?
You don't.
All right, so this should say, instead of substitution, just CPC. Okay, so there's your proof. All right, that's a pretty intense proof right there. Pretty intense
Once
proof.
you drew the line, I knew it.
Once you draw the line, then yeah, but who knew to draw that line? All right, and for some reason the book gives two other proofs for the same proof. All right, so this is just like the triangle one, except it's for the trapezoid. You get two things. You get that the median is parallel, in this case parallel to the two bases, and you get that formula.
So it just makes two of the trapezoids.
It literally makes two other trapezoids. Now, when we get to the area section, we might be able to say something. So, I don't know, can you buy that this one is half the area of the other one? That was a harder sell. But we'll save that for a different day. Certainly doesn't look like it. This is the last one. We're just going to do some examples here and we're done. We'll do 4 easy ones and 1 medium one. All right, we got the proof written down, or sorry, the theorem written down. Normally, Killing, you want the first one?
Sure.
All right, so how do we use this? We'll do a simple one first. Well, it doesn't say the set. The setup is this is a trapezoid, and the middle segment there is a median. All right, so the basic theorem said what?
That
It's
is
half.
Half of the
sum of the
basis.
bases.
So what are the two bases here?
47 and 13.
Oh, and then we got to do what with that?
Add them,
And then
get a number, and then you divide it by 2.
you got it. If I really wanted to write all the details, I would start with the formula. The formula says that the median, ST, is equal to the two bases added together divided by 2. Well, the two bases are 47 and 13. That gives us,
60,
and therefore the answer is,
30.
all right. Is that easy enough? Okay. Who wants another easy one?
And one hard one.
Easy one? All right, easy one. Easy, click, are you? There. Tell me what to do.
So let's say that ST is equal to ED plus FC.
Okay.
And we plug in.
I think it was KL though, isn't it?
Oh yeah. And then we plug in the number
Okay.
11, 13, 14, 20.
Therefore, KL is, all right, easy. How can I make this harder?
Equations.
All right. Or maybe I could ask for not the median, I could ask for one of the bases. So who wants that one? That's the big but here, is that it can be more complicated. This is sort of like, which one does the 27 go to? If you ever take a test for me and you're like, I'm not sure what you're pointing to, which one is pointing, make sure you ask that question.
Well, then you have to
All right, give me the setup.
GF plus
How about ZY equals,
GF plus HE.
all divided by 2. Okay, now let's plug in what we know. Well, this time we know what ZY is. It's, and which one of these do we know, GF or HE? Okay. It's clicking slowly today. Oh, crud. How do we solve this?
You divide 27 by 2 first.
You multiply
Oh,
27
yeah,
by
you
2.
divide
Multiply both sides by 2. The 2 would cancel on the right side. We'd be left with,
number.
54.
and then therefore it's pretty easy from there, right?
Yeah, and then you get 31.
All right. So that's how it's, those are the 2 flavors of easy, right? One more,
No.
McKinley?
Okay.
Tell me what I should write.
dy equals KL plus JM divided by 2. dy is 8.5, and KL is 7, JM goes down. Times 2 by 8.5, which gives you a number.
17.
That is a number. Then you subtract 7, which gives you 10, which JM equals.
All right. So the only way I can make this, I mean, I can't make it hard. The only way I can make it more challenging is give you variable expressions for things. Okay. So variable expressions. Oh, by the way, you just got to make sure that it is a median. It's a trapezoid with this median.
But we don't know if it's trapezoid technically.
Well, it says trapezoid with median.
then why do we need 7, 7, 6, 6 instead of 50?
Then just
Agreed.
confuse
Okay.
you with
All right.
that.
All right. Set it up.
Okay, sorry.
Oh, by the way, it doesn't give us any of the vertices this time.
10 equals 2x plus 4 plus x plus 3 over 2.
X what?
10 equals 2x plus 4 plus x minus 3.
Minus 3. Okay.
Minus 4 minus 3.
All right.
And then you add, and then you get 3. I'm just going to combine my terms first.
I would do that.
And you're going to get 3x minus 7 over 2, and then you get multiplied by 2, 20. Then you get plus 7, you get 27, and then you divide by 3 and get 9.
So x equals 9. Now this question, remember, it comes in 2 flavors. It'll say, what does x equal? Or it will say, how long is, I don't know, how long are the 2 bases? So how long are the 2 bases? How long are the 2 bases?
Oh, x plus x minus 3 equals 6. And then 2x minus 4 equals
So 6 and
14.
6 and 14. Okay. That's it.
Oh God, classroom answers.
No, I'm just saying that's it. You did them. I mean, these are basically the same problems, right? Just different numbers. I have more in case we weren't getting the idea. I don't want your homework. I'll just leave it up to you. I'm going to tell you, you need that table of pain in your notes, in your book of truth.
I already put it on.
Right? That way, your test is going to have a fair number of true, false, and one of those sometimes, always, never type statements for the quadrilaterals, and you'll need that table of pain to help you out.
Sir, I have a question.
What's up, Ben?
So on the homework, numbers 21 through 25 say, join in order the midpoints of the sides when you draw the, like for 21, you draw a rhombus, and then
Okay.
figure out the midpoint, and then you have to join the midpoints. But I'm confused as like, do I join it with its parallel, or like the opposite side, or do I join it going from like midpoint 1 to midpoint 2?
So it's literally saying, take the quadrilateral that's given. So like 21 says, draw a rhombus, find the midpoint of all the sides, and then play connect the dots. When you play connect the dots, it's going to make a shape, and they're trying to have you take a guess at what the shape is.
Oh, I see it, yeah. All right, thank you.
Cool. Catch you later.
Bye.